In this lesson, you'll learn about a very important register inside the central processing unit, called the accumulator. The accumulator is only one of many registers inside the CPU, so before we take a closer look at what it does, let's first answer the question, what is a register? A register is a very fast, temporary storage area inside the CPU. The contents of a CPU register can change millions of times a second while a program is running, so it must be designed for very quick access. A register can only store one item at a time. Depending on which register it is, that item could be a piece of data, like a high score in a game, or a program instruction, or the address of a location in the computer's memory. A register is actually a group of flip-flops. A flip-flop is an electronic circuit made by combining logic gates in a special way. But that's another story. What really matters here is that a flip-flop can be switched on or off. It can quickly flip or flop from one state to the other. So you can imagine a register is a bit like a group of light bulbs, and when it's storing an item, some of those lights are on and some of them are off. If a light is on, that is, if the flip-flop is on, it represents the digit 1, and if it's off, it represents the digit 0. A register is therefore a component capable of storing a group of binary digits. We call them bits for short. All program instructions and data inside a computer are represented as groups of binary digits. That's why we call them digital computers. Early computers had CPU registers that could only store 8 bits. A group of 8 bits became known as a byte. A register inside a modern CPU can store 68 bits or even 128 bits. It's not convenient for us humans to think in binary, so we can represent a register as a simple box containing a regular number, or a single program instruction. Now, take a moment to look at this simple computer program, written in a high-level programming language. A high-level programming language is one that humans can understand easily once they've learned how to code. Can you work out what the output will be? The program puts a number in each of the variables A, B, C, D and E. Then it adds the contents of these variables together and puts the result into another variable called Z. At the end, it outputs whatever is in Z. We're going to think about what's going on inside the CPU while this program is running. In fact, we're only going to consider what happens when one instruction of this high-level program is being executed, so we can focus on the job of the accumulator. Before any high-level code can run, it has to be translated into something that the CPU can understand. It first has to be turned into machine code, binary ones and zeros. A translator will usually convert high-level code into an intermediate form of low-level code first, before then converting the low-level code into machine code. You can see some low-level code here. Each high-level instruction becomes many low-level instructions, but then each low-level instruction becomes only one machine code instruction. By the way, every type of CPU has its own set of commands that it recognizes, for example LDA, STA and add, and a few others. These are known as the instruction set of the CPU. Because there's a one-to-one correspondence between low-level instructions and machine code instructions, it's convenient for us to imagine the CPU executing low-level code. After all, we humans are not very good at reading binary. So let's visualize these instructions being executed. You're going to see some of the events that take place during the fetch-execute cycle. We'll be focusing on just a few components of the CPU and how they interact with the main memory, namely the control unit and the Arithmetic and Logic Unit. The accumulator, which is a register located inside the Arithmetic and Logic Unit, and another important register called the current instruction register, which is located inside the control unit. Our program has already been loaded into the main memory. This is taken care of by an operating system, such as Windows 11, when the program is launched by the person using it. This program makes use of a few variables. A variable is a named location in the main memory. Each memory location has an address, which is actually a number, and memory addresses can be very big numbers. Even a modest 4 GB of RAM has over 4 billion memory locations. But most programmers don't need to concern themselves with numeric memory addresses because they can refer to memory locations with symbolic names like A, B, C, D, E and Z. When a program is translated to machine code, variable names are converted into numeric memory addresses, which are also in binary format. We're going to assume that the part of our original high-level program that assigns values to the variables, which is not shown here, has already been executed. So these variables already contain some data for the code to work with. The next step, then, is to fetch the next instruction. The instruction is copied from the main memory into the current instruction register. This is, of course, an abstract model of the CPU, which doesn't explain everything that's going on. For example, this model doesn't have any cache memory. Also, there are a few other registers involved in fetching an instruction. But it's okay to leave out some of the details because we're only really concerned with the role of the accumulator at the moment. The current instruction is now executed. LDA-A means load into the accumulator a copy of the contents of variable A. So the value 20 is copied from the main memory into the accumulator. The next instruction is then fetched. It's copied from the memory into the current instruction register, overwriting the instruction that's already there. Add B tells the CPU to add the contents of variable B to whatever's already in the accumulator. So the value 30 is copied from the memory and added to the contents of the accumulator by the electronic circuits inside the Arithmetic and Logic Unit. The cycle continues. The next instruction is fetched from the memory into the current instruction register, overwriting what's already there. This instruction says add whatever's in variable C to whatever's in the accumulator. So you can see that the accumulator is now accumulating the result of the calculation. The next instruction is fetched. Add D. The contents of memory location D will now be added to whatever's inside the accumulator. You can see the value in the accumulator is getting bigger and bigger. The next instruction is fetched. This time we're going to add the contents of memory location E to whatever's in the accumulator. You can see in this example the same actions are being repeated over and over again, which is why we call it the fetch-execute cycle. The final instruction is slightly different. Store Z is an instruction to take whatever's already in the accumulator and store it into memory location Z. So this time something is moving out of the CPU and into the memory. Here's a summary of everything you've seen. If you're a student of computer science, you might want to note these points down. A register is a very fast, temporary storage area inside the CPU that can store one piece of data, one program instruction, or one memory address. In the next video, you'll see some registers which store memory addresses. The accumulator is a special register inside the Arithmetic and Logic Unit of the CPU that stores the intermediate results of calculations while a program is running. It does exactly what its name suggests. It accumulates values. High-level programs are translated into low-level code, then binary machine code, and stored in the main memory before they can be executed by the CPU.